So in objective 1, the first thing is that you've got some questions, right? Some questions that are conceptual. So make sure you understand conceptual stuff. Things like if I pour 2 kettles of water at the same temperature together, what happens to their kinetic energy? Remember, kinetic energy is related to temperature. In fact, if you want to care, the equation is 3/2 RT. We haven't actually talked about that. So if they're at the same temperature, they have the same kinetic energy, where T is the Kelvin temperature. R is a constant. You've seen R before, actually. PV equals nRT, right? It's the same number. Okay, so the temperature here gives you the kinetic energy. So if they're at the same temperature, if you pour boiling hot water into boiling hot water, the kinetic energy doesn't change because it's the same temperature. But also the potato chip bag. What happens when you take it to a higher elevation? It gets bigger. Why? Actually, why? Why does the potato chip bag or the bag of yogurt, the thing of yogurt, you've done this before, when you came up from the springs, the yogurt explodes, right? Or the beer bag of potato chips, why does it get bigger? I guess because the pressure is lower. See, the pressure pushing out is the same in both cases. But there's another pressure. What is that? The pressure at low altitude is bigger and the pressure at high altitude is smaller. So therefore the bag expands. Okay? And then a lot of people are struggling with the second question, which is mathematical, which is super easy. What do you do there? You say you're going to convert atmospheres to torr to kPa. You just need to know that there's 101.32 kPa equal to 760 torr equal to 1 atm. So if I have 82 kPa and I want you to convert it to torr, what do you do? Dimensional analysis. Well, I got kPa. I'm going to write 101.32 kPa. And I'll put 760 torr. kPa cancels. 82 times 76 over 101. Or, if I have a more simple problem that you might get, if you've got 1.3 atmospheres and you want to convert to torr, you'll take 1.3 atmospheres over 1. 1 atmosphere is 760 torr. Take 1.3 times 760. Does that make sense? All right. The second objective, objective 2, was Boyle's, Charles, and Gay-Lussac's laws. These are so easy. You just have another laws. It's P1V1 plus P2V2. That's Boyle's. You didn't even know that it's Boyle's. You didn't even know the guy's names. That's not important. The second one is V1 over T1. This is Charles. That's V2 over T2. And then P1 over T1 is P2 over T2. Now what's the thing you got to watch? The units. The temperatures have to be in Kelvin. P's and V's need to be in the same units. Now you might get confused. Well, as soon as I got to convert to liters, I got to convert to liters because everything's got to be in liters. Not true here. Here, consistent units. I mean, if your pressure, one of your pressures is in atmospheres, and this is in millimeters of mercury, you're going to have to convert them to the same units. So it has to be the same units. Doesn't matter what unit. It could be in pounds per square inch. The volume could be in gallons. It makes no difference as long as you're consistent. But T's have to be in Kelvin. That's the only thing. Now, everybody good on how to solve mathematically for these? Cross multiplication for these, right? And, you're usually solving for either V or P. You'll divide, say, by V2. Both sides. If you're solving for, say, P2 or whatever. Solve for whatever you need to solve for. So these are, how can you recognize these questions? If I give you a P and then another P, you've got one of these problems, don't you? You've got two different pressures, or two different volumes, or two different temperatures. Okay? Do we need to do one of these, or you're good? You just plug it in the numbers. All right. Then the next one, go that way. The next one is the combined gas law. And that's, again, it's very similar. It's P1, V1 over T1. It's P2, V2 over T2. It's just putting all three of them together, right? In this case, you're going to have a P1, so have a V1 and a T1, and maybe a P2 and a T2, and you're solving for V2. I don't know, you might be solving for P2. You might be solving for T2. You're going to solve for one of the twos. So you have to decide which one you're asking, and then it's just some it's an algebra, right? You just cross multiply, right? P1, V1, T2 equals P2, V2, T1, and then solve for whatever you're solving for by doing good algebra. So if you have a number, let's say your pressure was 700 torr or something like that, your volume was 3 liters, your temperature was 300 Kelvin, that was your initial conditions, and then P2, we don't know what that is. Your new volume was 5 liters, and your new temperature was 400 Kelvin. How would I solve this problem? Cross multiplication. So then you could say P2 times 5 times 300 equals 700 times 3 times 400. Divide both sides by what? Now, you understand on a calculator, what do? You'll take 700 times 3 times 400, divide by 5, divide by 300. Divide. We'll go from the bottom. Once they divide times, you'll be off by 900 times. 300 squared. Make sense? When you do this mathematically, are we good on if I were to pull a calculator out? No? Ideal gas law. Well, you just got to know this gas law. What PV is nRT. So P stands for pressure. V is volume. Now P has to be in atmospheres. Now we have a limitation. It has to be in atmosphere. Your volume has to be in liters. So if it's not in atmospheres, convert. If it's not in liters, convert. You might be given milliliters. N is the number of moles. Sometimes you're given grams, and you have to do a gram to mole conversion. R, of course, is the gas constant, 0.0821, and the temperature has to be in Kelvin. It's very limited on what units you can use. So you're asked to solve, maybe for P, maybe for V, maybe for T, maybe for N. All right, so if you've got 3 grams of something, let's say 3 grams of oxygen, you're going to say 32 grams in 1 mole. And that will be then, this will then be your N. Right, when you get that, and 32, 3 divided by 32. So objective 5 was Graham's law. Everybody struggles with Graham's law. Actually, there's also Dalton's. Mr. Dalton. Dalton's law, he's just P total equals P, say of hydrogen plus the pressure of oxygen or whatever, and then you just continue to add them up. And everyone's missing the one question where if you know, they'll say if you have the total pressure, let's say it's 600, and you know the pressure of, say, the water, and you're looking at the water vapor pressure table and how to use that, then you would, let's say it's 30 or 27, then you would take, what's this one going to be? 600 minus 27. All right. For Graham's law, let's do Graham's law. He's the guy who's how fast the gases travel. So if you're doing a comparison, say, between xenon and argon, how much faster is argon? Is the lighter one. So argon on the periodic table weighs 40. Xenon weighs 131. Who's faster? Which one's faster? And we did this with a straw. Big ones are faster or slow ones? Or big ones are faster or small ones are faster? Small ones. So he weighs 40, so he's the fast one. Now how do you find out how much faster he is? You take the square root of the big number divided by the square root of the small number. Right? There are no units on this answer. Okay. So let's pull up the calculator. So I'm going to take the square root of 131. Hello, what did I do? Second square root. 131, close my parentheses, divided by the square root of 40. That's 1/8.
They just have way too. That or they just have too much alcohol.
1.8 times faster. Don't take 131 divided by 40, you get about 3. It's the square root. So is it 7.8, ladies? Good on this? And then the last question is stoichiometry gas law problem. Everyone's missing these up. You're going to have an equation. I'm going to say sodium carbonate plus or something like that. Let's say I say potassium chlorate breaks into oxygen plus potassium chloride. Let's say you've got 3.2 grams of this. I'm asking to find what is the volume of this at a pressure of 620 and a temperature of 25 degrees Celsius. What do you have to do? You're going to do P equals nRT, right? You've got a P, you've got a T, you're trying to solve for V, what do you need? And now you'll guess, what are you missing? How do you get in? I use this number. Oh, but wait, I have an equation. So what do I do? Stoichiometry? I've got to write a balanced equation. So I'll do this for potassium chloride, KCl3. K is positive 1, chloride is minus 1. It breaks into oxygen, O2, right? Plus potassium chloride, KCl, so K is positive 1, Cl is minus 1. That's an unbalanced equation. To balance this equation, I'm going to need a 2 here, a 3 here, and a 2 here. I'm going kind of fast, but I'm balancing the equation. These are not balanced equations. I know I've got 3.2 grams of this. I need to convert this to moles of oxygen. That moles then will be plugged into PV equals nRT. So I'll take 3.2 grams of KCl3. I have to do sort of mini stoichiometry. What do I do now? I'll say 122 grams of KCl3 and 1 mole of KCl3. Where did I get that number? Where'd the 122 come from? Molar mass of KClO3. I happen to know it in my head. That's it. I know it's the molar mass of KClO3. All right, then what do I do? Moles to moles. So I'm going to say 3 moles of KClO3. No. 2 moles of KClO3. 3 moles of oxygen. I then go to my calculator, and I'll take 3.2 divided by 122 times 3 divided by 2. Not an error. So 3.2 divided by 122 times 3 divided by 2. Notice I don't go an extra, a lot of people I'm seeing go an extra step. So it's 0.0393 moles. And we're going to do PV equals nRT. This has to be converted to atmosphere, so divide by 760, right? So I'll take 620 divided by 760, and I get 0.81. My temperature will be 298. I can do that in my head. So then I'm going to say P is 0.81 times V, I don't know what that is equal to N. N is the 0.0393 times 0.0821, that's R, and the T is 298. We then get our calculator and we solve V, so I take 0.0393 times 0.0821 times
It's 6 days.
298 divided by 0.81. Survey says 1 point.
Can't wait till I do There's nothing special about
Make sense?
it. Yeah.
There's nothing special about that.